Hi, so in this short video, we're going to talk about the concept of a z-score of a data. So of a data set, you're going to have a lot of points. Some of them are above the mean, some of them are below the mean. And in this session, what we're trying to capture is how far are the data from the mean. But our measuring stick is going to be one standard deviation. So you find the difference between the mean and the value of x, that's one data point, and you divide by the standard deviation. So you know, you're figuring it out, is it 2.2 standards above the mean? Is it 1 standard deviation below the mean? So dividing by the standard deviation will tell you how many standard deviation is that distance, right? Of course, there are going to be two definitions, one for the population z-score or a sample z-score. Depends on what are you working with. If you're working with population data, you use the x divided minus the mu, which is the population mean, divided by the sigma, which is the population standard deviation. If you're working with a sample, then these becomes the x bar for the sample mean and the s for the sample standard deviation. Of course, I just said this, if the value is above the mean, if x is above the mean, that distance is positive, so the z-score would be positive. But if the value is below the mean, then this difference would be negative. And it's okay. The z-scores could be negative. That will tell you that the value is below the mean. The z-scores are unitless, right? Because remember that the standard deviation has the same units as the data themselves. So these two quantities, when divided, if you keep track of the units cancel, and the z-score is just a number. Okay, something you can say the z-score is 2.3. The z-score of this value is negative 1.2. So let's do an example. A little bit about baseball. I hope you're familiar a little bit with the rules. I don't want to get a lot into that, but there are two leagues, the American League and the National League. In the American League, the main rule difference is that in the American League, the pitchers do not have a turn at bat. So whenever there's a turn for the pitcher to bat, there's another player called the designated hitter for the pitcher that he would bat whenever it's turn for the pitcher to bat. The National League, on the other hand, every player has to hit the ball, which makes a skill that is basic in baseball. So some of us prefer the rules of the National League. It makes to a lot of interesting strategies, because once you take the pitcher out to put a pinch hitter, then the pitcher cannot come in, so you have to do your strategy around that. If you have a runner on base and your pitcher's turn comes at bat, should you take him out for another hitter? So anyway, a few years ago, they changed a little bit of the calendar, and within the season, there are interleague games. So teams from the National League do play teams of the American League, and they follow the rules of whoever is the home team. But before that happened, they never played against each other. Teams in the National League only played with their rules among National League teams. Teams in the American League would only play among their rules with only American League teams. And the only place they would play against each other would be in the World Series, which is the final series for who's the champion of that year. So that's a little bit of context to tell you what's happening here. There are two in these two leagues, and in the season, the Boston Red Sox led the American League with runs scored with 949, but the Cardinals led the National League with 855. Now, this difference in runs scored is kind of expected because of what I said. The American League has an extra offensive player, if you want to say it that way, because they have a hitter that is especially just in the game, in the team, just for hitting, right? While the National League, they have like a spot in the batting order, which is going to not be so offensive. So it's natural that they have less runs scored. Now, so this is not comparing apples to apples, so it's not a fair comparison. So let's go a little bit more in detail. In the red, I painted a red and blue. So in the American League and the Red League, the mean, I call it mu A, was 811, while in the blue, in the National League, the mean was 750. So again, it's kind of normal that to happen because the National League has less offensive players. But the important thing is how far are the teams from the mean of their own league, right? So in the American League, for example, they scored 949 runs, and the mean for their league was 811 with this standard deviation. While the National League, it was 855 with this mean and that standard deviation. So now that we know the means and standard deviations, we can capture how far are they in terms of their own league in terms of the z-scores. Yeah, so if we calculate the z-scores with these numbers, we get that the Boston Red Sox were 1.87 standard deviations above the mean, while the St. Louis Cardinals were 132 above the mean, 1.32 standard deviations above the mean. So now it's a more fair comparison, like among their league, among their peers with the same rules. It's still going to be true that the Red Sox are farther removed from the league than the than the Cardinals, right? So now we can say, okay, the Red Sox were a better run producing team or a more offensive team in that league. So comparing z-scores gives you a little bit more context to compare apples to apples, or at least among their same in the same with the same rules. Everybody now you're saying, okay, this was 1.87 above the mean. The other one was only 1.32, so the Red Sox do stand out about it. So you go to z-scores when you want to compare more, something like that. Now we use also z-scores in some textbooks, stuff like we call some values going to be unusual. It's not a term that is like straight across the board to use, but in some textbooks we like to do this. So we said that we talk about the empirical rule already. So when you have a curve that has this shape, and this is the mean, and you have a mean plus standard deviation and mean plus 2 standard deviations, and you go to the left, mean minus standard deviation and mean minus 2 standard deviations. So we know that 95% of the data are right here, right? So 95%, so in terms of z-scores, that's just a -2 and a +2, right? So z-score would mean your 2 standard deviations to the left or 2 to the right. So then we can say, well, if you have a z-score of more than 2, that would only happen 5% of the time, right? Because between these two values, these two tails, if there's 95% in the middle, there's 2.5% over here and 2.5% over here. Because in the middle, there is 95% of the data. Let me bring this with me to the next slide. So we're going to use this to be called an unusual value. Somebody that's outside of 2 standard deviations will only happen, adding together, right, will only happen about 5% of the time. So if you have a value that is whose z-score is more than 2, you're not on either side, then we'll call that an unusual value. Okay, this is the term that is not straight across the board, but in some textbooks we use it. And if it's more than 3 or less than 3, then remember that captures 99.7% of the data, and then they're going to call that a very unusual value. Okay, so sometimes they can ask you a question: is this value unusual in this data set? What we need to do is find the z-score, and it's above. If it's more than 2 or less than 2, it's unusual. If not, it's not. Okay, so this is how we start this short video.